Hello, everyone. I'm from China. In fact, I don't know I should say good night or good afternoon. You know, Moscow time is 5 hours late than Beijing time. So it's 6 p.m. in my hometown. So let's begin. My topic is about how Tencent use PGConf in WeChat payment system. At the beginning, let's introduce Tencent and WeChat payment. Tencent company is one of the most popular and the biggest internet company in China. It has more than 20,000 employees. And WeChat is the most popular social network application in China. And it's also the latest product of Tencent company in social network area. WeChat payment is the wireless, fast, secure, efficiency payment solution provided by WeChat. At the end of 2016, WeChat payment has 600 million users per month. And at present, we process 50 million transactions per day. Okay. Let's come to the first question. Why we use PGConf? Okay, PGConf is our internal name of PGConf. PGConf is an open source MPP solution, cluster solution. And why we choose PGConf? First, just now I said the data set is huge. Every year we have 30 terabytes data, and the data sets keep increasing. At present, we cannot have a single database instance to handle such big size. And then PGConf has SQL interface, and the SQL interface is more flexible and popular, of course, compared to key value solution and other solutions like HBase. And the third one is PGConf can handle complex query, especially join across nodes. And PGConf also can provide consistency of transaction. So it's easy for our application to use. And also, it's about the through output of transaction. At present, per minute, the peak transaction we handle is 1.5 million. It's quite a lot of transaction. And also, because our business and our customers keep increasing, maybe from 2015 to the end of 2016, the transaction we handled just increased by 4 times. Yeah, 4 times bigger than the beginning of 2015. And so we need the capacity of horizontal scale out. Okay, this slide just define PGConf cluster. So it provides SQL interface, easy to use. It can handle complex query, join over multi-nodes. Also, we are concentrating on the OLTP workloads at present. And then is MPP, massive parallel processing architecture. In the cluster, we have, of course, the PGXC cloud architecture is very similar, or you can see very little different from the PGXC one. In the cluster, we have coordinators, data nodes, and the data node has standby. Standby, we use hot standby. So, coordinator, it provides access entrance over the cluster, and it also handle data sharding when new data comes into the system, and when handling query, it also route the query to the correct node where the data reside. Also, it handle tuples from multi-nodes in one cycle. About the schema or catalogs, coordinator only has catalogs. It didn't store user data, so it's lightweighted. Then the data node. Data node stores real application data, and it processes the DML options against the data reset in the node. Also, besides this, data nodes also handle the replication, I mean the log shipping to the stream node. Last one is GTM. GTM means Global Transaction Manager. It manages transaction traffic and provide the consistency management of transactions. Finally, it's about the catalog. So we have one copy for every node. It means every node has a copy of schema, and only coordinators have global catalog information, and every coordinator, the catalog is the same. They have identical catalog. Yeah. After the introduction of PGXC architect, I will introduce some internal technology. First, I should. This is the background technology. When our system is initially built, we have got only 16 nodes in all. But at present, when our business keep growing, we have more and more data to store. So we need to scale out our system. But the system is an online service. It's payment system. We cannot stop the system to scale out. So we have to scale out our system when it is running. But PGXC, if we want to scale out, we have to stop the cluster, dump data, add new nodes, and then re-import the data. This is unacceptable for our application. So we modify the data routing strategy. We introduced the middle layer we call shadow map into the system. The shadow map just map the we call it the hash value, a hash value to the specific data node. It means if we add new node into the cluster, we didn't need to rehash all data. We just need to rehash the data we want to. I mean, very small part of the whole. Okay, Then this is the online scale out steps. We have a monitor system. This monitor system is a management system of the whole cluster. The monitor system just, we can interact with the system. We told the system first we add a new data node to cluster, and then make a plan of moving data to new data node. This plan consists of several data moving tasks. You can see we have several. Maybe at present we have many tasks. This task is from this task means we move data from the source node to the target node. And one task can move several shards. But one data move task is an automatic one, an automatic operation. It should be succeed or failed. No other situation, no other status. Okay. This is about. This is the detail of each task. At the beginning of the task, we just dump the stock data from the source data node. In this step, we should acquire a snapshot of the node. The snapshot ensures there's no overlap or miss between stock data and incremental data. After this, we also use the snapshot to start logic decoding. Logic decoding is a new feature we added to 9.3.5. Okay, just now I missed something. PGConf.Russia is based on Postgres-SQL 9.3.5. In 9.3.5, it didn't provide logic decoding feature. We added it. Yeah. Then the second step, we just restore data to target data node. After this, we have a iteration loop. In this loop, at the beginning, we just get the new coming data from source data node, and then restore the new coming data into the target data node. At the end of the iteration, at the end of the loop, we check the new coming data size to compare to a parameter to see whether the new coming data is little enough. If it is, we just break the loop and go into there, block writing at the source node, and then upgrade the routing info of all coordinators. Then we just, after this all, we release the blocking. We can see all through these 5 steps, we just block at the end of the step. Yeah. In the final step, we block. That block will last no more than 30 microseconds. So it can ensure our service is running always online, no interruption. Yeah. Continue. After that, I will introduce some multi-group technology of PGConf. In WeChat payment, we have many merchants. These merchants have data of different size. Some huge merchants, especially the shopping website or the banks, their data every day coming to the system will up to more than 30 gigabytes per day. But in 2015, at that time, we use PCIe Fusion IO SD card to store the data to just ensure the performance. But at that time, the storage card larger than one terabyte is much more expensive. So we choose the card of capacity with 1.1 terabytes. But for a single huge merchant like shopping website, Jingdong, it will run out of the data storage of a single node in 1 month, and we have no solution because the data are keep coming into the system. So we have to provide a solution to handle such huge merchants. We call it data queue. So we just divide the data nodes inside the system into 2 groups. One group, we call it small k group. Merchants inside this group are merchants with much less data than the huge ones, and so we can store its transaction data inside one data node. But for the big one or the huge merchant, we just store their data inside the big K group. In the big K group, we distribute the data of one single merchant into different data nodes. We use the day offset of the create time of the tuple as a factor to determine which node the data should go to. I mean, the big merchant data generated in same day reset at the same data node. It means, for example, today the merchant data will come into node 1, but tomorrow it will come into another one, different data node. By doing this way, we just balanced the data across the whole group. After this, no matter how big the merchant is, we can store the data and handle the transactions. Okay. We have another multi-group technology. This technology is for cost saving, because we know in China, government have the laws for security industry. We have to keep the transaction data for several years. But the most active data is from the latest several months, maybe 3 months. So access to this data, just maybe the ratio is 95%. But we have keep all of them. But and the whole data set is pretty big. If we just store them, we use the same hardware, the cost is much higher. So we introduce the cold data group strategy. Cold data group means we just use low frequency. We just store low frequency data inside the high volume hardware. But in the hot data group, we use high performance hardware to store the high frequency data. And by doing this, we can reduce the cost by 60% of the whole system. Okay. After the 2 multi-group technology, the whole PGXZ WeChat payment cluster looks like this. At the top, the first layer is a coordinator. In coordinator, we use the create time of the tuple to determine we should go into hot group or cold group. After this, for example, in BK list, sorry, it's a mistake. It should be small. Okay. In BK list, we use merchant ID to determine the data should go into small group or big group. And we can see here, each group has its own shard map, and it has only one shard map. Most amazingly, our application didn't need to know the storage details of the data. They just access the whole cluster the same as they access a single Postgres-SQL instance. This is the value of the solution. Okay. The next, I will talk about a small plan optimization of order query. This is especially for huge merchants, because huge merchants every day they have more than 3 million transactions per day. But they need to. Sometimes this is pretty often. They want to know. They want to know the incomes of the past months. Every bill listed by the finish time. And this query is triggered by a website. And the operator is there. So we should return the result as soon as possible. You know, 1 month we have 90 million rows. We should return the result in less than a second. You know, I think it's not easy to do. So we just did some customized optimization for this SQL. At first, we partitioned the table by month on the fcreate time. And then we create a multi-column index on merchant ID and finish time. Finish time will be used by the order by clause. And this is the detail of the plan optimization. In coordinator, we push down the limit of site clause to all data nodes. And inside the data nodes, it uses the index we just created to scan every partition. And when returning data, we use merge append operator of PostgreSQL. Merge append will ensure the output of the operator is well sorted. So by doing this, the output of one single data node is well sorted. And inside coordinator also use merge append to combine result from all these data nodes involved. By doing this, we can return the data. Return the result in a very short time. This is the result. We can finish querying in less than 50 microseconds, and at most we can handle QPS of 5,000. Okay. Another issue is about the load balance. You know, the data node, the primary data node, has heavy workload. even at the peak time. And we have some offline task. I don't think they should. I don't think they must be run on the master node. So we move them to the standby node. But we cannot access the selected node directly. We need a coordinator. So we introduce a read-only coordinator to do this. Yeah. The read-only coordinator is catalog just point to the entries of host standby node. By doing this, we can balance the load from the system well. Another issue is also about load balance. This issue, I think, maybe many of Postgres users will have. In our system, especially in the payment system, every transaction we have many updates. Because of MVCC, updates will create many versions of data. This will cause auto vacuum run very frequently. Yeah, auto vacuum just produce many Xlog. And we need archive this Xlog to the offline disk, just in case of disaster. But these two network workload plus together, it will run out of our network resource, and it causes the system unstable. Yeah, just wave up and down, very bad. So we just move the archive Xlog feature to the standby. Of course, the community did not support this. We modified the code. I think maybe we can contribute the feature to the community. Okay. This issue is about the online table reorganization. We know we can use cluster or vacuum for to reorganize the data, the table, but the vacuum for will block any transaction on the table. Yeah, especially for us. The system is running online. People are paying through the website. We cannot just block them. We need to run every minute, every second. And so we just introduce the online table reorganization. We call it vacuum for concurrently. It means we can run the reorganization or vacuum for online without blocking service. This is the first background technology. It's about open-only heap mode. PostgreSQL use free space map to manage the disk space. In the free space map, we cannot know which tuples are new coming tuple. So we introduce the append-only mode. Append-only mode means when we switch on the append-only mode, all data coming to the heap will be appended to the end of the heap, like that. The right one is the new coming one. So after remembering the block number of the whole heap, and we can know which rows are the new coming ones. This is the second background technology. It's a shared CTID pipeline. Just now I said we cannot block our service, but we have to synchronize the modification or the new tuples to the new tuple, because we are running vacuum for. But we have to ensure the new coming tuples are correctly inserted to the new heap. So we introduce a shared pipeline. The general general PostgreSQL process, they are running updates. They just insert their new updated tuple into the pipeline. They write into the pipeline, and the vacuum full process, they are running parallel. Yeah. They just read the data from the pipeline. By doing this, we can ensure every modification, every new tuple into the source table or source heap will go into the correct place. Okay. After these two background technology, we'll come into the detail. This is about the online vacuum full step detail. At first here we just use a low-level log to build a new heap. Of course, the new heap is based on the catalog of the source heap. So we just copy the catalog into the new heap. And after we build the new heap, we build the new indexes of the new heap. These indexes are also based on the source indexes. After this, we switch on append only. So at present, until now, we didn't block any updates or any DML of the heap. And then when go into heap copy, this step is the real hard one. And at first, we just use the common step, copy stock data atom by atom into the new heap. After this, we finish the stock data copy, we rebuild index on the stock data. And when this is done, we go into an iteration loop. In this loop, we have two steps. Step one, we read from the shared pipeline to get the new coming tuples and apply the change on the new heap. After this, we will check whether the data change is small enough. If it is, we break the loop and upgrade the log to block DML. Until now, before this, nobody know we are running. Nobody else know we are running. We are running reorganization. Until now, we block them. But the data size is small enough. The change apply didn't last long. Maybe no more than 1 second. Yeah. After this, the turf, the hardest thing is done. And we go into here. This is much easier. Just swap table refile node, swap index refile node, and drop the original table. The whole process is over, and we have finished the reorganization. Okay. For payment system, it's about money. So we have to provide high availability. In China, we have to provide disaster redundancy across cities and IDCs. It means we have to provide high availability between at least 2 cities and 3 IDCs inside these 2 cities. So we can see here we have 3 IDCs, Shenzhen 2 IDCs, IDC 01 and Shanghai IDC 2. Our service is deployed in Shenzhen. So this is a master data node. Every master data node have 2 slaves, one synchronized, one asynchronized. Besides this, in every IDC we deploy coordinators just to ensure if any of these IDCs is down, we can provide service through the other coordinators. Above this, we use inside every machine, every node, we use agent. We use agent to collect status, to collect and report status of one node. And above the agent, we have judgment center. Judgment center is used to collect all data node status. It means every judgment center has the whole view of status of the system. But only one. Here you can see we have 3 judgment center, but only one is master. The others are hot standby. And we use Zookeeper. We use Zookeeper to decide which judgment center is the master. It means if the master is down, Zookeeper will choose any hot standby to be the next master. This infrastructure can ensure any one of the IDC is down, the system is running well. Even 2 of them is down, we can provide part of the service. Yeah. Okay. Here is about the PGXZ cluster of WeChat payment. At present, we have 2 GTMs, 7 coordinators, and 31 pairs of data nodes. And but at the beginning, when the whole cluster is initially built, we have only 15 pairs of nodes. So in the past 2 years, we scale out almost 3 times, and we will scale out next month too. Okay. Next step job. First, we try to upgrade PGXZ to 9.6, all may rebase on PGXL. And we will try to contribute vacuum for concurrently to the Postgres-SQL community. Okay. Okay, this is my team. They are very glad to see you guys. Yeah. And in the end, I'm from China, Shenzhen. Yeah, it's a warm city, pretty warm. Almost 26 degrees now. So when I came to Moscow, I was very sick. Okay. Anyway, you're welcome to Shenzhen, China. When you get there, just contact me. I have my email there. We can have a dinner together. Okay. Okay, thank you. Any questions?
Did you try open source solutions for online vacuum full, or you start rewriting new or you start writing your solution? I mean, solutions like PG repack.
In fact, we didn't try that. Why we developed the feature online vacuum for? One reason is to reorganize the table. The other reason is we want to, MVCC will just use more disk space than it indeed need. So we want to reclaim the disk space.
I know what vacuum full does, but I mean there is open source solution like PG repack for doing that already.
I'm sorry, we didn't try it before.
Okay.
About PG repack, we use it on production, and it's good. We have no bugs about 2 years maybe.
Great.
You will see on this extension, it solves this problem.
Okay.
Any more questions? Okay, let's say thank you to our speaker.